so this idea of a standard position has to mean that the initial side, which is one of the rays of my angle, is lying on the x-axis with the tail of the ray usually hanging out at the origin, as in the case right there. And then you have what's known as the terminal side, and that's the other ray that creates my angle theta. So theta is a Greek letter that we use to denote an angle, but you could also use alpha or theta, other Greek letters. And the terminal ray, this red one, is where I end. And you can imagine the terminal and the initial ray kind of being stuck with a pin right in the middle, right there. I can spin that red ray all around multiple times. I can go counterclockwise with it, I can go clockwise with it, and I can create angles. So terminal, where I end up with my angle, initial, lying on the x-axis. That's standard position. We have 4 specific terminal side locations that we want to emphasize, and that's what we know as called quadrantal angles, or angles on the quadrants. So we're going to talk about these quadrant angles of 90. Terminal ray is vertical. 180, terminal ray is pointing opposite direction of the initial ray. 270, pointing down vertical, and then 360, I'm winding back up exactly in the same spot as the initial ray. Yes, Sam?
Can you go back a little bit?
Yeah. All right, so quadrantal angles, you'll hear me refer to them both ways. Angles that are on an axis. And as we go through this, you're going to see that we create, when we're not lying on an axis, we create triangles with my initial ray and my terminal ray. And that's what we're going to use to study our trig function. You good, Sam?
Yeah.
Okay. So a lot of upfront information, just some FYI. Here's some more. Measures of angles. So we can measure angles in degrees. You guys remember the days when you had the protractors? Yeah, we have some of those people use, but protractors, we measure angles in degrees. You can measure angles in what's known as a radian, and this is probably new to us. You guys probably have not heard of this before. Maybe you've heard of it, but just didn't know what it is. So in a degree circle, you have 360 little parts, 360 1-degree angles. That would create this circle all the way around, 360. And then in the radian world, we don't talk about it in degrees anymore. We talk about it in terms of radians. And there is a relationship between radians and degrees. And we're going to learn how to convert the one from the other, because that's going to be important for us to be able to do that. But definition of a radian, here it is right here. The measure of the arc of a circle. What's an arc? What's the arc of a circle? No idea.
The round.
Yeah, it's the round part of what we call a sector. A sector is a slice of the circle. So an arc is like the crust on a pizza. And a sector would be the slice of the pizza. So when we say the measure of the arc of we're talking about that right there is my arc. Now you can see that an arc can be actually anything from just above 0 degrees and then all the way to 360. Actually, I can go all the way around and still have an arc of 360. It's just one of the full circumference. Correct? Anything else? Yeah. All right, so this concept of a radian, we're going to measure that arc, the length of it, and then we're going to divide that by the measure of the radius of the circle. So the radius of the circle, again, goes from the center out. So when the radius length and the arc length are the same thing, so let's pick a number. Let's say the radius was 5, and my arc length was 5. then that would mean the angle that they form. So let's just, we're putting numbers in here. That's 5. And then this arc length is also 5. When that happens, then you create this angle theta in here, which is a radian. And it doesn't matter. Now, do you think that that changes whether my circle gets small or large? If I made this circle big, does it change that angle theta there? No. The size of the circle does not dictate the length or the measurement of an angle or in degrees or in radians. That's not a big deal. The rays still stay the same position. They just, the arrowheads get longer if I have a bigger circle, radius-wise. But the angle itself stays the same. So a couple things you need to know when we talk about radians, and we're going to do a little video blip here, a little web blip. Exciting video. But first, let's talk about this thing called the unit circle. We're going to be using this a lot. A unit circle has a radius of 1. And then, why do we need to know circumference? Because that relates to arc length. These distances along my circle, right? So if I know the radius, I can find the diameter. Either of those two can allow me to find circumference. Now, circumference has another equation. What is it? Pi d or 2 pi. Good. Bueno. All right, there we go. So my radius is 1. I have a diameter of 2. What's up? You all right with that?
Yeah, I was like, well, how does that mean? So, radius times.
Exactly, radius times 2 is what d is equal to. Correct. Very good. Okay, so let's take a look. Here it is. What is a radian? There is a visual of it, right? We described radius length, and then that's the red, and then that same length applied to the arc, which is now in blue, creates this angle. Maths is fun. Yeah, somebody who is not an English person actually created that website. Maths is fun. Yes. What were they doing? Maybe there was already one that was called Math is fun. So they just put the Maths is fun. I don't know. Maths is fun. All right, so visually, in degrees, that's what a radian is, 57.2958. It's a irrational number. Just keeps going. 57.2 roughly. 0.3. But here's a little blurb. It's pretty cool. So what is a radian? Well, there's a pen that measured the radius, and then we took that radius length and we wrapped it around the outside of the circle, giving me what the radian measure is. Yeah, pretty cool. That's pretty cool. Okay, let's see that again. There's the radius. Let's take it. Oh, amazing. I can't slow. That is incredible.
So
what's that? So a radian is a.
So a radian is the length around the.
No, that's not a radian.
Of
What does it say a radian is?
the angle.
The angle.
Made. Of
The angle made. So a radian is an angle. And how many degrees are there in an angle of a radian degree? We already said it's 57, but here's how you break it down. We take 3 radians, and there's a little more left over. That gets me to 180. That little bit that's left over is 0.1459. That's equivalent to 180 degrees, which we know is pi. So take that. Get 37.295. That's how many degrees radian. All right? Yes?
How many numbers of pi have they found?
How many numbers of
Like,
pi?
they just have, like,
Only one number of.
No, but like continue.
Oh, you mean how many have they gone out?
Yeah.
Well, it's a good question. I'm not sure. I really don't know.
Some pretty. They have just like computers that just like calculate.
Yeah, but that would be a horrible waste of time and a misuse of the computer. To calculate the non-terminating decimal.
Well, it could terminate somewhere.
Well,
Our lines would explode.
Yeah, I guess you could blow your mind. Terminate the decimal somewhere.
Exactly.
All right. So that's what a radian is, the measurement other than degrees. Let's close. We want to close that one. Any questions for radian before we move on to the new? So there's just a little over 3 of them. It takes me to a half of a circle. All right. So here's another way of measuring angles. It's called degrees, minutes, and seconds. This is what we would do in engineering when we were doing land development. Degree, minutes, and seconds is a way of expressing decimal degrees. So DD, decimal degrees, DMS, degree, minutes. So degree, minute, second, what does that break down to? If you take a 1 degree angle in a circle, and you broke that 1 degree angle into 60 equal little parts. Those little parts, 1/60th of a degree, would be equivalent to what we know as a minute. And then if you took one of those 1/60th parts of a degree and you split it into 60 equal parts, then you would have what is known as a second. So degrees and minutes and seconds is a way of expressing angles in a obviously more detailed. Obviously, all of our angles don't just happen to be perfect integer numbers, right? So sometimes they're decimal equivalent. So degrees, minutes, seconds, decimal degrees. This is how we can deal with that. So here are some examples here of breaking down one form to the other, going from degree, minutes, and seconds to decimal degrees. This guy. Here's what degree, minutes, seconds looks like. So it uses the degree symbol, obviously, for degree. The minute symbol is the apostrophe. That is apostrophe. And then the quotation mark is your seconds symbol. So seconds and minutes. All right, so 22 degrees, 14 minutes, 38 seconds. Well, how much of a minute is 14 seconds? Roughly. Let me rephrase that. How much of a degree would 14 minutes be? There we go. Start there. If there are 60 minutes in 1 degree, 14 is about, somebody said it, a fourth of your degree, right? So how do we convert from one to the other? Well, here's the breakdown. The degree number stays, and we're going to add to it this quotient that we have here, something over 60 for minutes, something over 3,600. Now, why is it 3,600? You know why? 60 times 60. If you have 60 parts creating a minute, and each of those little parts has 60 seconds in it, 60 times 60, 3,600. So you just take the minute number, divide it by 60, you take the 38 seconds number, divide it by 3,600, you're going to get some decimals. You add those decimals all up, now you're in decimal degrees. 22.240. And these can be, you'll have to, sometimes they don't terminate, or maybe you just go out to the fourth sig fig or something like that. Sig figs. What about going the other way? This one's a little more, I'm going to have to think about this one a little bit more. When you're going from decimal degrees into degree minutes seconds. So here we have 74.1469 degrees, and we want to convert that into 74 degrees, so many minutes, so many seconds. Now, when we do this, we're going to usually, the thing that might have a decimal in it will be seconds. Minutes will not. Degrees will not. But the seconds can have decimals. So how do we do this? This 0.1469 number, the decimal part of the decimal degree. We leave the 74 as a 74. That becomes the degree number. We take the decimal part, 0.1469, and to make it into minutes, where the other time we were dividing by 60, now we're multiplying by 60. So that's what happens here. So 0.1469 times 60 produces this. An 8.814. Now I put a 0 in front of that because minutes, usually you have 2 decimal places, right? For minutes, ones place, tens place. So if I did 0.1469 times 60, I'm going to get 8.814. The decimal part of that, 0.814, now gets multiplied by another 60. And this is now taking me into the seconds. So the 0.8 part of this now becomes, you notice this part becomes the minutes. 74 degrees, 8 minutes. And then the 0.814 times 60, I get this new number down, 48.84. And we leave that as the number of seconds. Okay? So take the decimal part, multiply by 60 once. Take the decimal part of that, multiply by 60 again. And then I am now in degrees, minutes, and seconds. Not that hard. It's just if you don't do it, practice, it's not going to be. So it's kind of an FYI. I want you to just be familiar with degree, minutes, and seconds. Understand if I give you something in degree, minutes, and seconds, what I'm asking you to do with it. Oftentimes we're converting it to degrees, decimal degrees, and I need you to be aware of how that happens. All right? You actually have a function on your calculator that does this for you. So I'll show you that later. All right, moving on. Remember, we got a short period today, so we're going to fly. So negative angles. Positives and negatives. How do I know which is which? When we're talking about an angle rotation, we are talking about what's known as a polar angle. And in a polar world, what happens is angles rotate either counterclockwise or angles rotate clockwise. And when you go counterclockwise, that is a positive angle rotation. You think, oh, wait a second, should it be there? No. Counterclockwise is positive. And when you go clockwise, it's a negative angle rotation. Now, we always start, I specifically use the right side of the axis here, because in a polar world, that's always 0. Unlike a bearing. A bearing is another way of measuring direction, but that's a compass. And a compass actually has north, south, east, west. And where do you think 0 is on a compass? Yeah, it's on the top. So in a compass or bearing, this is 0, and then this is 90, and then this is 180, and this is 270. So that's for like navigational purposes. Whether you're nautical versus on ocean type stuff or airplane, you use bearings. But we're going to talk about polars, and they start at 0 here, and then this one becomes 90 if we just work our way around. 180, 270, back to 360, because remember 0 and 360 are the same thing. It's supposed to be a 0, not a 6. Yeah. Yeah. So we can express angles in positive and in negative. And then also, hey, what about something like this? That's bigger than a circle. So what does that mean? What did we do? We overlapped. Yeah, we overlapped. We went around in multiple revolutions. What this one? Multiple revolutions. So 450 would start at 0 and go around to 360. One rotation. And then what do I add to 360 to get to 450? I add another 90 degrees. And is that not right? No. Yeah, that's right. 450. 450 would be hanging out right here. So it's on the same location as a 90-degree angle. Or, let's talk about, we didn't do this one yet. We didn't do this one. Forgot to do this one. So negative 25. Negative goes clockwise, positive goes counterclockwise. Negative 25 would just rotate in this world over here. That's negative 25 going that way.
Arrow there.
You don't have to put the arrow there, like over here on this one, the negative 520. We won't put the arrow. How do you know it's negative?
How do you know it's negative? How do you know?
Well, one of the ways we know it's negative is because there's a negative in front of the degree.
Well, I'm saying, but if you were just looking at it.
Right. Yeah, if I was just looking at it, like let's do it for this one. So negative 520. Negative 520 says go clockwise around the circle until you get to the equivalent of 520 degrees. Well, we know we're going more than 360. Well, how much more are we going? We can figure that out. Just do a little simple. What am I doing? I'm going around 180, 160 more. Going around 160 more. But I'm doing that in the clockwise direction, not the counterclockwise direction. So, how do we write this or show it without using negative? So I'm going to go from 0. There's negative 360 to there. And then we're going to go another 160. Well, 160 is going to lie somewhere over in what would be our quadrant 3. It's going to be over here somewhere. Looking like that. 20 degrees less than if I were to be back at that 180. Negative 180 takes me back to the horizontal.
Okay.
So if I drew something like that, where you see the arrow going clockwise, you know it's a negative angle.
Right.
Otherwise, we would have to write, hey, that's a negative 520 degrees in here if we're supposed to be dealing with negative angles, right? So one of those two ways, either how we rotate it, or actually physically see the negative in front of the angle. Okay, so multiple revolutions, negative angle rotations, positive angle rotations. Those are all putting me back in the same location. And if I were to do that, like for example, let's talk about this one, this 450. So we did a positive 450, and we said that positive 450 put me at a 90. So what these are, 450 and 90 are what we refer to as coterminal angles, because they end up at the same spot. So coterminal means you have the same terminal ray. So you can see there's multiple answers for all of these. Two angles with the same terminal ray. Right? So again, 450, 90, coterminal angles. One of them went around multiple times. One of them went around just 90. I could also say the negative 270 is a coterminal, because that takes me negative world, supposed to be back to the same spot. All right, questions? Any questions so far? A lot of review stuff. Or maybe, is this review for you guys? No. Oh, well, never seen any of this. Well, all right, all right. So make sure you're stopping me if you forget to stop. All right, converting. So this is probably like the main point of this section is how do we go back and forth from one to the other? And you're going to have a lot of different formulas you're going to have memorized by the time we're done with chapter 6. Here are the first two. You must know how to convert from radians to degrees or from degrees to radians. Right, so I would definitely put these, if I've got my flashcards, some of you guys might be flashcard people, or some of you might have the back page of my notebook where I put all my formulas I have to know. This should be them. These two should be them. So here's the best way to remember how I set it up. You notice that they both have the same ratio, but just reciprocals. They have this converting factor right here that involves a pi and a 180 somehow. So how do you know which one has the pi on top and which one has the 180 on top? Well, if you're starting in degrees, you want to have the 180 on the top because degrees on the top means pi or radians are cancel. And vice versa. If you have radians, if you have radians and you want to get degrees, you would have 180 on top. If you have degrees that you're starting with and you want radians, you would put pi on top. Now pi, we can express radians in terms of pi, meaning we leave pi in answer. But pi is the same thing as 3.14 blah, 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 radians. So if you don't see a little degree symbol next to an angle number, it's understood that it's in radians. It doesn't have to physically say radians. See the degree symbol, you know you're in degrees. So you just want the units to cancel. If I have radians, I want pi on the bottom so that the radians cancel, leaving me with just degrees. And that's probably the easiest way to remember how you set it up. Where do you start? Where are you beginning with? And I want to get rid of that. So in this first example, we want to change 75 degrees into radians. So I'm starting with degrees, which means I want to get rid of degrees, which means I better have degrees show up down here. And then what goes on top of this pi. Now notice this one says leave your answer in terms of pi. Don't convert pi to 3.14. Do a little simplifying here. So I get 75 pi over 180. Let's see, 5 goes into both of those, so we can at least go to 15 pi over 12. No, 36. What am I thinking? 36, thank you. And then 15 and 36, 3 goes into both of those. So we can take ourselves to 5 pi over 12. That is what we say leaving your answer in terms of pi looks like. Reduce your fraction, leave pi. That's actually a more exact answer than converting pi to a decimal and then going out. Now, not all the time we'll be able to leave things in terms of pi because maybe I didn't start with pi. Maybe I started with actually a physical decimal radian number. And in that case, we just end up with a radian or a decimal answer instead of a pi answer. What about going the other way? Started with radians, so I want to end up with degrees. So that means my degrees needs to be on the top, and my radians need to cancel with each other. So I have this. And I want radians to disappear. That means pi needs to be down here now. And 180 show up. Okay. Pi's go away. And then I have 180 over 18. Leaving me with what? Degrees.
If I was supposed to say change back to radians.
Those radians. Oh. Oops. Yeah. Because it started in radians, right? So I want to change those degrees. We good? Yes. Oh, I just was lazy. It's still there. Okay, last one. You guys should try that one. Now notice this one doesn't have a pi in it, so convert it. So 5 radians. Again, there might not. We're looking for for the symbol, and I want degrees out of this. So I want 180 on top over pi. And then, yes, this is 900 over pi degrees, but we want to make it decimal. So we got, what was it again?
286.48.
There you go. 86.40. All right, just for purposes to kind of gauge where you are. 0 degrees, 90 degrees, 180, 270, and then 360. All right, 90 degrees is the same thing as a pi over a 2, which is 3.14 over 2, or 1.57. So we're just kind of getting an idea, radian-wise versus degrees, what do we have? Pi is half of a circle. So that's pi right there. And we know pi is 3.14. A half a pi plus another pi is 2 pi over 2. Plus another pi over 2 is 3 pi's over 2. So if I had 1.57 plus 3.14, I'm going to end up with 4.71. So that's the number of radians there. And then if I add 3.14 twice, taking me back over to 0, I get what's known as 2 pi, or 6.28 radians. So those are just some numbers that might be helpful. Okay.